Hi, I'm Alex Russell. I'm a software engineer on the Chrome team here at Google. And before I joined Google, I worked on a JavaScript framework called Dojo with my friend Dylan and Tori here. Um, and once upon a time, the browser was a gigantic black box to me. Now that I work on the inside of the browser, I thought I would come back over and smuggle out some of what I've learned about how it all actually works from the inside. Not because I think it's particularly interesting in some academic way. It's generally not. There are really interesting problems inside of a browser. Like if you think about the sorts of problems that we solve in a browser, the things that I can think of in computer science that we're not actively working on include large-scale distributed storage and artificial intelligence, and that's about it. Everything else from low-level graphics to storage to virtual machines to memory management to security, threat isolation, process isolation, multiprocessing, fast inter-process communication, pretty much languages, pretty much you name it, we're doing some of it inside of a browser. So browsers have a lot of interesting problems in there, but like the reason we're all here today is because we want to build things for browsers because browsers have been successful. Okay, let's get to it. I want to tell you about how a browser actually thinks about the things that you send it, because it's important. Because the apps that you build are probably going to be everywhere. Web apps are going to be everywhere, if they're not already. So we have a new class of sort of, I don't want to call them closed, because they're not. They're more open than the things that came before in terms of handsets. But there's an app ecosystem world in which it kind of mirrors what happened on the desktop years and years ago. And now we've got a chance with the web, once again, to sort of break that open and use more open and interoperable technology to help deliver great experiences everywhere again in a multi-user way. A lot of things that the folks like David and Yehuda have been talking about all day to help you get the advantages of a web-based, network-based application without having to rewrite it a bazillion times. Great, that's good. So that's what we want. That's the thing. But we want to have a 60 hertz UI, right? We want to have everything on the screen showing up one frame after another, probably 20 milliseconds between frames or less, and we don't want any hiccups, right? The last thing we want when we're going and building a rich user experience is for there to be a hiccup. That's sort of the definition of something going wrong in your app, right? That's what feels janky. We use the word jank on the Chrome team to describe when something just sort of hiccups or doesn't work right. So what we don't want is janky UI. So I'll use the word janky a lot. Great. So I want to talk a little bit about our constraints. Today, on the mobile world, we've got 500 megahertz to 1 gigahertz CPUs, mostly single core, mostly ARM, right? So these are not the same CPUs that we've known and loved from the desktop world. They're different. We've got somewhere between a 16th and a quarter of the RAM that you can get on a low-end netbook today for not very much money. For a device that costs more to manufacture. And we've got GPUs that are, frankly, very modern, but at the same time, they have limitations that we can talk about a lot more about in a minute. But let's just compare and contrast this with the desktop that was just delivered to my desk a couple of weeks ago. I got a brand new Mac Pro. It's got dual quad-core i7s in it. It's got a separate bus for memory access, a separate bus for graphics access, and a separate bus for I/O, right? So the CPU can talk to all these different things without sort of any of these big hiccups in the way. That's pretty good. The graphics card has something like, I think it's a low-end graphics card, so it's got something like 512 meg of memory on the graphics card. That's what these things have top-end in the whole device. Like this has got a 512 meg of, this has got as much RAM total as my graphics card does at work, or as my laptop has. So we're talking about a totally different class of runtime that we would like to deliver the same 60 hertz experience on that we've built the rest of our web experiences that we've come to know and love on top of. So that's all right. The GPU number here looks pretty impressive. 7 to 90. That's not 70. That's 7 to 90 million triangles per second. So let's compare and contrast a little bit here for a sense of scale, since most of us don't think of that number. That's roughly what a PS3 will do at the top end. Like we're in spitting range of a PS3, right, or an Xbox 360. So we're talking about several generations old in terms of hardware design, probably 2 or 3. So that's what we've got access to, best case on the mobile world. Okay. So that all sounds like we're doing pretty well, right? I don't know about you, but like when I started programming for the web, my desktop was a 90 megahertz Pentium Pro, maybe Pentium, something like that, 66 and then overclocked or something. You know, I had 48 or 60 some odd meg of RAM, a graphics card that was separate from the CPU, was sort of a fantasy, something that you ran Quake 3D on. Anyway, we're now in a place where the stuff in our pockets is really good, but it has these new limitations that resemble very old computers too. So storage access is really, 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 really great. In fact, storage access, because it's mostly flash, looks a lot more equivalent to sort of main bus access as it might have a couple of years ago. But unfortunately, we have the return of the unified memory architecture, right? So like you would expect an old Intel, 950 chip, integrated graphics chip to sort of like make your little core netbook feel slow because it was sharing the same system memory as everything else. That's the same architecture that we've got on these devices, right? So in many cases, we're sharing the same memory for everything. Everything, graphics, code, data, everything you're using is probably going to be in the same graphics pool, in the same memory pool. So remember that when you send something to the GPU, you didn't send it very far. You may still be allocating memory against your application. And the OS are using very aggressive memory reclamation, right? Because we don't have very much of it. So OSs are GCing applications in the background. Many OSs aren't allowing you to run real background applications. Those are the sorts of constraints that web applications now have to live under, and we don't have a lot of signals that are getting passed back to us as web application to know that we're in trouble. So what are our coping strategies? One, we can anticipate the platform, right? We can go and we can build things that are designed for these constraints, and we can design from the bottom up with them in mind, assuming that this is the new baseline. Or we could try to get more signal, right? And getting more signal is going to require us to run more code. And as we'll talk about in a minute, running more code is probably shouldn't be our first option. Okay, let's talk for a minute about the networks. So let's assume for the moment that not everybody in the world is on Wi-Fi all the time, or that their application isn't always local. This is the great benefit of having wireless connectivity everywhere, is that you're always connected. So having your app being able to update all the time, having it live in the cloud, this is awesome. This is an outstanding benefit to your users. But the RTT is really terrible. So the round-trip ping times that are measured on most 3G networks look something on the order of 100 milliseconds to about a second, right? 80 to 800 is sort of the general range, but 100 is on Verizon, 80 is sort of AT&T's lower bound, right? These things all have stories behind them. They're all about the internal network architectures and the amount of deployed hardware on the ground for each of these networks. But let's call it a lower bound of about 100 milliseconds RTT, right? So what does that mean? Like I don't think all of us think about our days in terms of that. 100 milliseconds is about half the time that it takes to get from here to Australia, right? This is about coast-to-coast round-trip time in the continental United States if you've got a relatively poor connection. So this is like here to New York and back, say, making a detour in Saskatchewan, right? I mean, that's roughly what we're talking about at the best case. Usually, you'd think on the desktop that that's a pretty poor experience, and that experience is connected to a much more ballsy computer, I'm guessing. Okay, 200 milliseconds is the RTT to Sydney. So we're talking not quite the distance to the moon, right? But you can think of your sort of like worst case user experience for making any single network request that requires a new round trip as something close to a second, right? So count on that being something close to a second. That's really bad, right? really, really, really expensive. So if there's nothing you take away from this discussion the rest of the day, just remember that the cellular modem in here makes your app slow. So the less that you request a new resource, the faster your app will be. The more you can send things down as one single chunk, one single request, the more you can bundle stuff together and send it all down as one payload, the better off you're going to be, because these numbers are daunting and they're not necessarily going to improve, right? So what we've gotten a lot of is significantly better bandwidth, available bandwidth, in terms of the ability for the networks to start carrying more bytes once you've set up a connection. But that initial round trip time, that latency, hasn't significantly improved, and it's not clear that it will. An interesting side note, because of the way TCP works, we actually may not see the benefits of that improved bandwidth until we see significantly reduced RTTs. So the fact that you've got a 4G modem and it says you're going to have such and such bandwidth may not actually show up until you have lower ping times to start with because of the back-off algorithm. Okay, so that's the baseline. That's the hardware. That's what we got to work with, right? That's the baseband. That's the OS. That's the stuff we've got down there. What about the browser? So I can only talk about WebKit because that's the only browser that I've ever worked on. But I should say that WebKit isn't a browser. WebKit is the engine that powers a bunch of different browsers. And we'll talk today about why WebKit isn't a browser is an important thing to keep with you. I work on Chrome specifically, which is not a mobile browser, but it uses the WebKit engine, and I can talk a lot about how Chrome plugs into the network and the disk and all the other parts as a proxy for WebKit, and how all the other browsers that you're going to be encountering on the mobile that use WebKit do exactly the same stuff, and the sort of trade-offs that they're going to be making on your behalf to get there. Okay. Also, if you have questions, we'll take them at the end. I'm going to save a lot of time for questions. This shouldn't take too long. So WebKit is not a browser, right? WebKit is a web rendering engine. It is a pile of code that has a zillion little things that you can plug into it. And as a browser vendor, you actually have to plug in many of them. Some of them are optional. Some of them are totally required. For instance, image decoders. WebKit ships with its own set, or if you go and download the source, it comes with its own set of native image decoders. But most every browser that I know of uses their own set of image decoders. They go and they say, our platform supports this, or we've got some specially optimized library for ROS, something like that, and they plug in their own image decoders. Similarly, most browsers wind up plugging in their own native theme rendering for things like buttons and scroll bars, that sort of thing. They wind up either proxying back through to native controls for that or doing all this other stuff. So what happens here is in WebKit, WebKit takes the content, does all the layout, does all the sort of coordination at the center of the process of getting a page and rendering it for you. And then it calls out to all these other little bits and says, give me what I need so I can present or help you present a coherent picture of everything that's happening in your app to your user. And we'll talk about how all the different parts of the stack wind up as these little things that you plug in, including things like JavaScript, which is incredibly important. All right. So what does WebKit actually do? It's an important question because everybody talks about it. Everyone's like, WebKit this, WebKit that, WebKit this, WebKit that, right? But WebKit is not a browser. So what does WebKit actually wind up doing all day? WebKit is the thing at the center. WebKit drives the life cycle. So if you think about this in terms of maybe a widget framework that you know and love, right? You wind up with some initialization phase that you drive, and then it does some stuff, and then it calls you back at some other places, like it's an event-driven thing, and then it winds up giving you a thing that you can go put someplace else. That's exactly what WebKit does, but for entire web pages. So WebKit includes a bunch of machinery to help you manage the life cycle of requesting resources, which you then plug in your own network layer to, requesting resources from cache, which you plug in your own cache layer to, requesting DNS lookups, which you plug in your own DNS lookup system to, requesting parsing for CSS, which it does itself, and HTML, which it does itself, JavaScript, which it can do itself, but you can plug in your own, on and on and on and on and on, decoding images, the whole bit. And then eventually, WebKit comes in and does a couple of passes, and we'll talk about those. But what WebKit doesn't do at the end of the day is actually send the bits to the screen. That's another one of the pieces that WebKit will hand off to you. WebKit doesn't actually have a built-in way to send you bits to the screen. You have to plug in your own low-level rendering layer to make WebKit draw anything anywhere. And that's actually one of the things that causes the differences between WebKit-based browsers for things like canvas rendering, for instance. Okay. So there's a lot of stuff that WebKit doesn't do. And I'm not going to cover all of it. I'm just going to cover the stuff that I think is sort of top of mind as we talk about how to build performant mobile web apps. So let's look at, to understand exactly what's going to happen here, let's look at how you requesting a page results in WebKit doing some work, because I think that might be the way to illustrate the question of what is WebKit doing for me lately most coherently. All right. So I'm online, and you can be too. So if you go to google.com/codesearch, you'll see something like this. I actually went to this to code search, and then I clicked on well, there was a Chrome link over here, and then I clicked on WebKit, and now you can both browse and search the WebKit source tree. Right. This is probably the fastest way to get around any public code repo, including the WebKit code repo. This thing is invaluable. Recommended. Fire it up. Follow along at home. All right. Cool. Oh no. I needed that. All right. All right, so what happens? You start a request, which is to say something says, "Dear WebKit, please go get a page." So WebKit thinks of everything in terms of a top-level navigation initiated from a page. So in Chrome, we think of this in terms of like there's a tab thing, and the tab thing says to WebKit, "Hey, I need you." Here's a rendering context. Here's some initialization. I need you to go get this page. Here's a URL. Please go get it for me. WebKit then calls back into whatever the host is and says, "Hey, host, please go get this for me." It seems a little bit circular, but in order for WebKit to really understand what's about to happen, it has to sort of be driving the rest of this lifecycle. So bear with me for a minute. We say to WebKit, "Please go get me the thing." WebKit says, "Please go get us the thing." We go get the thing through a series of potentially slow operations. The first of which is DNS Lookup, wherein almost everybody goes and asks the operating system directly underneath you, "Please go get the IP address for this URL or for this host." Okay? We come back with an answer, and then WebKit says, "Awesome, I know where to go. Here's my disambiguated URL. Please go fetch this resource from that host." Right? It's going to form an HTTP request. It's going to send it down to you. You're going to do whatever you want with it. Send it off to the network, and then eventually you're going to set up a TCP connection using the underlying OS stuff. You're going to set up like the bits of the HTTP connection that WebKit wants you to, and then there's going to be this HTTP handshake, and then eventually content's going to start coming back, right? So at the point where WebKit has done all that work on the browser, you'll get an HTTP request on your server, and then you'll do your work, send something back. WebKit takes that back as chunks, parses it, and then independently of parsing, does this step called layout, which is, I think, the cause of a lot of consternation and confusion amongst web developers about what WebKit does or doesn't do, what's fast, what's not fast. So we'll spend a lot of time talking about that. And then independently of laying things out, it renders stuff, or rather, it asks you to render stuff based on a structure that it creates. So how does this all get kicked off? This is an eye chart, and I'm not expecting you to understand it. What I do expect you to take away from this is that it's actually very complicated. A lot of it's made complicated by the fact that in many of these places, we're calling back into host-provided stuff. So there's all of this sort of glue layer where you'll see something delegate in the C++ classes that represent the thing that WebKit is going to be asking you to go do work for yourself about. All right. The key part here is that there's something called a frame loader. The frame loader is the piece here in WebKit that actually is responsible for making that request back to the host and saying, "Dear host, I'm going to need you to go get this resource." So the frame loader is the core thing which drives both the cache and the networking lifecycle here. This is all available from the WebKit blog. I just stole this SVG. So, all right. Okay, so let's talk about the first one of these potentially slow operations. DNS, if we're lucky, comes off the local cache, right? So what we want almost all the time is to be going and getting the DNS from the local cache. That doesn't happen all the time. When it doesn't happen on desktop OS, sometimes we get lucky, right? Sometimes you've got a hierarchy of caches close to you that'll tell you the right answer in very low time. Unfortunately, this sort of hasn't been historically true. So last year, I think, Google launched the Google DNS Project to help get you faster DNS results closer to where you live, almost physically in many cases, because it's important to do anything on the web or on the internet that your DNS be fast. And so OS caches are relatively punitive. They wind up caching resources, a very limited number of resources, in some cases as few as 100, for not very long, like an hour or two. Like if I go to Yahoo and then the OS gets the IP address for Yahoo, an hour later it's going to be coming back to the network and asking me for yahoo.com. I just told you what it is. A lot of this has to do with DNS expiry. So in order to improve the ability to do DNS-based failover and round robin, a lot of sites have started to implement shorter time to live on their DNS records, which means that you have to go ask them again for the DNS much more frequently. So DNS turns into a big component of most web page loading time. So remember that that was slow on the desktop. Now imagine that round trip time that we're talking about from mobile network devices, and then put that in front of every HTTP request you're going to make. It's pretty bad. Hopefully your edge network has good DNS caching. Hopefully your 3G provider is doing a lot of good work for you there, but let's not count on it. So we want to alleviate the cost of that. For the top level requests, there's not much we can do. Hopefully, if you've come from someplace else, if you've clicked on a link, the browser can be smart. It can start to prefetch DNS records based on a hover or a tap or something earlier than you're actually navigating to the site. But for your own content, when you're sending a page down the wire and there's other things in your page that you know you're going to need from either a third-party domain or from some other server that you own that it's not on the same top-level domain, you can use the link rel DNS prefetch in Chrome and WebKit to help you go prime the cache. Put this as early at the top of your page for the servers that you're going to be requesting sub-resources from as possible. Please, please, please do this. Do this early. Do this often. Preferably in the first packet if you can. I'm not lying. If you can do this in the first packet, everything will go faster. Okay. All right, so we get DNS. We start making another outbound request. And then we get some HTTP lovin'. That doesn't include gzipping. So let's say I send an HTTP request out. I'm sending all my cookies. I'm sending all the state that I've got, including whatever HTTP headers you've sent along for the ride, post data, all the encoded stuff that you send along. And eventually, you get something back. Well, even if you say that you'd like the content of that request to be gzipped, the headers themselves are not gzipped, right? HTTP today does not have a way of dealing with the metadata being compressed. So there's an effort underway here at Google called Speedy. We're working with it in the Chrome project. Mike Belshi and Roberto Payan are doing amazing work there to help both enable this sort of compression and reduce the number of round trips you have to make for most common case stuff. But until Speedy is everywhere, be very careful about how much data you're sending back in headers and how much you're storing in cookies, because that is going to be penalized across every request that you send on both sides of the request. Okay, cool. All right, so okay, we get some content back. That's pretty good, right? Our server did its work. You know, it did a bunch of ORM stuff, made a bunch of queries. You know, hopefully wasn't terribly slow. It came back and it said, "Hey, here's a web page for you." Now, because browsers evolved in a time where networks that they were attached to looked a lot more like networks like you get on this than they do on your desktop, browsers start to do everything as soon as they possibly can, because they can't assume that you're going to get the answer back fast, right? If you've got some US Robotics 56K modem, you may not get the contents of your yahoo.com back in a timely fashion, depending on network weather and all of that. So what happens is today we've had a decade or so of experience with very high latency connections, specifically intercontinental connections. And what we know is that the content that comes back tells us a lot about what we're going to need in the future. So you know how I said that you could put that link rel prefetch or DNS prefetch at the top of your documents? You can do something very similar by putting resources that come from other domains towards the top, as long as they're not going to block. Because in WebKit at least, and now in most modern browsers, we look through the content as it's coming through before we may even have parsed it for rendering, and we try to figure out looking far ahead, hey, is there something in here that I'm going to need? And we try to go get it early. We try to start going and before we actually need the thing in the process of constructing the visual layout, we try to figure out if we can use what you've sent back to go fetch sub-resources. Okay, so let's go look at the code because I promised we would. And because it's actually fascinating. So browsers sort of seem like magic, but they're not. Browsers are not magic. Browsers are just C++, which is as close to magic as I think you can come in the form of a programming language, but they're not magic. Okay. So HTML document parser pump token has grabbed some stuff back. Like there's a tokenizer that comes through, and we come through and we know that we don't have to be synchronous. There's a bunch of stuff that happens. From the tokenizer, we get the next token. We try to do something, right? We try to construct a tree. Well, what's that tree? That's the DOM tree. This is actually how the tree of HTML entities gets constructed, out of which we construct the DOM tree that you're going to script later from JavaScript. So, all right. Later, we come through, and things can stall the parser, which is pretty bad. Note the when waiting on script or load to run, right? This should be a big tip off here that scripts may not be your friends. All right, let's come through here. Is waiting for scripts. This is pretty bad. So what does this mean? This means that if you just put a naive script tag at the top of your document here, we probably can't continue to look through the rest of the document to understand what's going to happen. Because there's an implicit contract. In the early days of the web, there was this API introduced called document.write, which made every C programmer feel very happy because it meant that you could treat your document like it was a stream. And I understand streams, right? I've got a byte-oriented thing, and I can write to it. Sweet. I got some byte-oriented thing coming back across the network, and now I can write to that too. What it means, unfortunately, is that in order to understand the contents of the document, which is what we're trying to do in the parser, we need to know what the next set of stuff is going to be. We think we know because something came in from the network potentially after that script tag ended, but we don't know that we know because you might document.write something into it, which might offset that stuff, which means that we'd have to come back through, and it might change the meaning of everything below it. So if you say document.write, or you threaten to by putting a regular script element in your page, there's very little we can do to come help you out of trouble. Now, there's an out. You can put the async and defer attributes on your scripts. Webkit now understands them. Most Webkit-based browsers do the right thing, which means that this will return false, which is great. Because what we want to do is come back here, say, no, we did not write HTML, and then continue tokenizing. That'd be great. That'd be awesome. OK, sweet. Where was I? OK, so Webkit then tries to predict the future by coming through and preload scanning. Right, we come through the document, we look at the tokens you've got, we say, hey, do any of these things, whether or not they turned into DOM tree yet, we don't know if we can use them, but did any of these things go and potentially need another resource? So there's this scanner that comes through on the side and looks and says, does this thing is it probably going to generate a request for other resources? We do something very similar for CSS. You can look through and there's a CSS preload scanner here. The CSS preload scanner does the exact same thing, but for add import rules, right? So if you have an at import rule right here, see that? The add import rule? Yeah. That's how we know that we can start to prefetch the stuff that was in add import rules. So again, this stuff isn't magic, but for years it didn't exist. So in other browsers, remember the add import rule might block page loading. The scripts might block all prefetching. And in fact, unless you async and defer your scripts, you probably will. OK, right, back at it. As we saw, scripts block, and things that block suck. So what blocks? Well, obviously, we talked about DNS lookup. We can't do anything until we have some content to work with. JavaScript parsing and compilation block. All right, what does that mean? So, and what do you mean by parsing and compilation? So these things didn't used to necessarily be different, right? JavaScript engines were evaluators. They would take some content in, they'd tokenize it, they'd parse it, and then they'd start running directly, right? They just start evaluating expression left and right. It's just as soon as you had an expression to evaluate, off they went to the races. Today, JavaScript engines have gotten significantly more complicated, which is to say they run a lot faster. And as part of that, they now parse and compile separately, and the compilation step can be significantly expensive. The compilation step actually turns into a gigantic trade-off. The work that was just done in Chrome in V8 in Crankshaft. V8's the engine that Chrome uses for JavaScript. The Crankshaft work is explicitly designed to allow us to trade off more time in compilation for things that we know are hot, whereas before we had to spend as little time as possible in compilation so that we could get out of the way fast. Because if we spend all the time that we know we're going to need to make code really, really fast, it's going to take a long time to compile. So there's definitely a time trade-off here. And if this is happening in the way of your scripts running, which is to say in the way of your application booting up, that's bad. So what we want to do is have a way for your scripts to get parsed as fast as possible, to get compiled as quickly as possible, and then to run as fast as possible. But there are serious trade-offs to be made here. It's worth noting that on mobile devices, you might think that your script is running fast. You might think that it's relatively cheap if you load it up in your desktop OS, but this parsing and compilation step can be significant. If you're pulling in a regular desktop-oriented JavaScript library, expect pain, right? The parsing and compilation, before you even start evaluating any of this stuff, before you even start running a line of code, just pulling in the code itself can be hugely expensive. So some folks on the Gmail mobile team and Charles Jolly, while he was still at Apple, did some great blog posts last year talking about hacks for pulling in script that don't involve having it pulled in with a script block specifically, so that you can pull them in, have them cached, or use them locally out of comment blocks as a way to get them pulled down, get them available, and then only run the compilation and evaluation step when you need to. Because that parsing and compilation, whether or not you know you're doing it, can be significantly expensive. Okay. So I want to talk a little bit about, we mentioned that there's a bunch of stuff in Webkit that you can swap in and out. One of those things is the JavaScript engine. Now, there's a long history at this point of JavaScript engines sort of sidling up to Webkit and going, hey, buddy, you got a DOM for me? And one of the very first was KJS, the JavaScript engine from the KDE project where KHTML, which then became the Webkit rendering engine, sort of evolved from. KJS morphed into Squirrelfish and then Squirrelfish Extreme, and then now I guess they're calling it Nitro. Basically, JavaScript Core, the Apple-provided and implemented JavaScript engine, which is very, very, very fast these days. Now, JavaScript Core evolved sort of in that straight line, and as a result, it came from an interpreter. KJS, and then JSC, and then Squirrelfish. These were all regular bytecode or straight-up interpreters, which means that there's no big compilation overhead up front for them, right? As soon as they get code, they can start doing something with it. There's a difference in kind here, though, with the Nitro and the Nitro Extreme, or whatever it's called this week, in that they have a JITting engine behind them, which means they're spending potentially more time compiling in order to get a JIT version of a particular function. All right, so what about V8? V8 only has a JIT. V8 doesn't have an interpreter. V8 does not have that sort of get me out of the gate fast version. All the other engines that we're seeing today from Mozilla and Microsoft sort of have that interpreter plus booster rocket on the side version. V8 is working it the other way back. They're saying, aha, what we're going to do is we're just going to JIT up front, and we're going to try to find a way to make compilation cheap, a la Crankshaft. So what does this mean? It means today that if you're using a device that's got V8, you're going to have a JITting JavaScript engine. If you're using a device that doesn't have V8, who knows? You might be in interpreted mode. Memory constraints might dictate that the size of the compiled code is too expensive. There are write execute questions about pages in iOS that might make JavaScript compilation untenable for the foreseeable future. It's not clear what's going to happen there. The result is that there's a wide performance differential, both at parse time potentially and at runtime, between these different JavaScript engines, even though they're all wired up to the same version and potentially share all the same other infrastructure in WebKit. Right, so keep that in mind. Right, when you're writing something for one of these JavaScript engines, it pays to go time how long it takes to parse and compile your code, as well as how long as it takes to run it. It's much harder to get a handle on that today, but please, please, please pay attention. Set timers up front, set timers at the end. Make sure that you know how long you're actually spending to go pulling your scripts, because you may not. All right. Synchronous XHRs, everybody knows how evil and bad those are for performance. They're much, 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 much worse when you have an 800 millisecond RTT. Okay, all right. Let's talk about rendering, because this is where all the sexy happens. Tokenization and parsing generate a DOM tree, right? That same DOM tree that you come through with JavaScript later with jQuery or Sencha or Sprout Core to go build beautiful things out of is the exact same thing that we go and build out of the HTML deserialization process. All right, so that DOM tree is what we then use to do layout. So what's layout? Well, layout is the process of taking all the stuff that you said that we're going to need to do in order to get you your CSS properly computed and all of the bits of absolute positioning and relative positioning, get that all figured out so that something can come through later and then turn that into bits on the screen. So that includes things like text layout, things like figuring out how long a line should be, doing the calculation to figure out, generationally how tall or wide a table should be, doing the constraints for min width, max width, width, natural width, all the sorts of things that you specify in terms of the layout of your application in CSS, we come through later and apply. So let's look at what actually happens here, because I think this is instructive. CSS isn't constructed the way I think a lot of us expect it to be. The way CSS is applied, this is the match rules method from CSS style selector. Right, this is the core thing. The CSS style collector class in Webkit is the core thing that goes through and actually does the work of turning the CSS that you've loaded into the document and doing stuff with it. So quickly, you get a DOM tree. At some point, we figure, hey, heck, let's do a layout. And what the layout pass goes through all the elements that we know we probably have to do something with, like whether or not we've loaded new CSS, or we've changed some property. We know that something is dirty, right? We keep track of whether or not something happened such that we would have to go do another layout. If we don't have to, we won't, right? We're not going to do this work unless we have to. But if we do have to, we come through, and then for every element, we construct a list of properties that apply from the CSS perspective, right? That means that there's all these rules that you set in your user agent style sheet, or in the document style sheet, or in a local style sheet, or on direct style application on the element itself. All that stuff has to get computed. Well, how does that happen? Well, we go through all the elements, and for each element, we look at the bottom of it, and we look at the rules one by one, and we look at the right-hand side of the CSS rule. This is critically important to understanding how CSS performance is affected. We look at the right-hand side of the CSS rule, which is to say the thing that's most specific. And what we do is we come through, and we grab if it has a pseudo ID, we do something with that. We get the pseudo rules, we try to match them. We get the tag rules, we get the universal rules, and then we wind up walking the parents, right, in order to figure out, for all the rules that we don't have an answer to yet, what else do we need to do? So CSS is designed to work bottom up, not top down, which means that the more specific, like let's say that you're using an ID rule, right? If you're using an ID rule and that element has an ID, we're going to match that first. We are going to be in and out of that CSS style application for that rule as quickly as possible. So let me put this another way. If I have a CSS selector that's written as .foo space .bar space pound thinger, and I'm matching any element, and that element doesn't have an ID, I never get through this, right? That's pretty good. And if it does have an ID, I match that rule early. So I can know whether or not I need to consider the rest of that rule to the left or discard it in this list of things that I'm applying. So CSS application happening from the bottom up is critical to understanding the performance of CSS style application. Which this also means that what we do is we walk, because of the specificity rules in CSS, we walk from that element as we're applying rules. Like if there's something we didn't actually get an answer to, we walk up the DOM tree. So CSS rules that are applied higher up can potentially be more expensive. This explains why deep DOMs and lots of rules can potentially hose the layout performance of your application. Does that make sense? Right. Think of it this way. The deeper the DOM, the more CSS rules you have loaded, and the less specific the terminal term of the CSS rule are, the slower it's all going to be. Cool? Right. Okay. What else is slow? Style readback. That is to say, if I say document.defaultView.getComputedStyle, and I grab the width property from some element, or I grab the offset the margin offset or the offset top, or any of the other computed real-time style values from any element. Remember how I said that we try not to do layouts all the time? Like, we're not continuously computing whenever you do anything in CSS, what all of the rules are that apply to that element all the time. We want to batch that up. We only want to do it occasionally. We want to coalesce as much of the application of those CSS things that just streamed in, because they might invalidate each other. So we want to do that occasionally and not all the time. Let's say, I'm measuring the document body, and I've got a bunch of new CSS that just came in off the network. Well, in order to get the actual width of it, I need to go and compute what happened to everything else in the document now. Well, the next time I come back and do that, if nothing else came in off the network in terms of CSS, or I didn't change any CSS rules anywhere, it's going to be blindingly fast. Why? Because we didn't have to recompute anything. We knew that we already knew the answer. So this helps explain why when you're going and you're using offset width, that sort of thing, you can sort of see this really weird, seemingly painful and inexplicable difference in performance when you're going to the DOM. Basically, anytime you read back a style property, not something.style, but like offset width or computed values, whenever you read those back, we have to go flush all of the pending CSS stuff and do a layout immediately. So remember, it's a good idea to try to get an answer to layout questions after the browser already knows them. You can do it today by using one of the new Requestanimationframe things, because we'll know sort of what the state of things are, or look for an onResize event. Look for your next onResize event. That'll tell you that something in the document resized, and that we now know the layout of pretty much everything. Reads against computed style should be relatively cheap then, unless you go do a bunch of work in your own scripts. Make sense? Sweet. All right. All right. You know how I said that we do pretty well with partial application of stuff? We wait 250 milliseconds. That's all. So we send out a request for stuff, and then we say, well, we're going to need to lay out something. We probably don't have the whole document back yet. But if we get the whole document back in less than 250 milliseconds, boom, it's there. If not, we're probably not going to paint much until such time as this timer fires, and then we're going to paint when we get new stuff to apply. Does that make sense? So if you see this behavior where you think you're above the full time is in one case relatively snappy because you're sending it all back in a couple of packets on a fast network, and then in another case, you're seeing this thing where, well, I get something above the fold in about a quarter second, and then stuff starts filtering in, and it's a little bit janky. That's what's going on, right? So keep your main payload small. Get it on to the browser so we can know that we can paint it immediately. Get on it. Get those payloads across and keep them small. All right. So Webkit is opportunistic. All right. So now we build this DOM tree. What happens? Right, we have to render something. We create two trees. We create a DOM tree, which is the thing you interact with, and then we create this render tree. And the render tree is the result of all that calculation for CSS style application. We actually create a different tree of objects. And if you have something that doesn't necessarily render on the page, it doesn't show up in this tree. This tree is the thing that another process comes through later and turns into bits, because this has all the information about line box widths, font sizes, rendered sizes, border sizes, margin sizes, padding sizes. Something else can come through and take that as a series of instructions to go paint using some low-level paint library in order to just start drawing bits on the screen. And that's exactly what happens in Webkit. Which means that those backends can be swappable. That's pretty good. Chrome uses Skia on Windows and Linux and Core Graphics on OS X. And Android uses Skia. iOS uses Core Graphics and Core Animation. Safari uses Core Graphics and Core Animation. There's a similar sort of setup in Mozilla where they use Cairo in many places. They punch holes into the Cairo backends for a lot of stuff. So now they can do GPU acceleration by sending primitive blitz to Cairo, and then Cairo can turn that into direct write or whatever. That's pretty cool. So we talked earlier, I think, in both the Sprout Core and the Sencha Touch presentation about GPU accelerated transitions and CSS animations. And we might have heard mentioned something called the Compositor. I don't think we did today, but there's something responsible for this that's called the Compositor. And I'm going to end with discussion of what GPU acceleration actually means, because we've gotten from the place where I make a request, I get DNS resolution, to I'm putting stuff on screen. So our whirlwind tour of web rendering is almost complete. But let's talk about what GPU acceleration means. In WebKit, it has a very specific set of connotations. The most complete version of GPU acceleration that I can imagine is something similar to what IE9 is doing today, where instead of taking some series of objects on the screen and treating it like a 2.5D scene graph, where I've got some things that are above other things, and then I just move those big things, for every single drawing call, you dispatch it to the GPU and say, you figure it out through some low-level graphics API. Windows happens to have sprung up one of these low-level graphics APIs that's GPU savvy in the Windows 7 timeframe called Direct2D. Voila, Windows 7 and IE9 don't. IE9 doesn't support anything below Windows 7 or Vista with the Service Pack, right? Like, if you happen to have this infrastructure laying around, it's really easy to use. WebKit isn't necessarily, and the platforms that WebKit runs on aren't necessarily blessed with 2009 engineering. And so what's happened is that we're approaching it from a different place where because of the constraints of the mobile platform and because of the available underlying stuff, what we're doing is, in some places, we're punching holes directly down to the GPU, right? So for things like WebGL and for hardware-accelerated Canvas, we're actually turning those draw calls into the low-level draw calls that you expect. For a lot of other things, though, what we're doing is we're sort of taking that 2.5D scene graph that you can think of the web page as, and we're saying, in some cases, yeah, treat that square, because most everything on a web page is sort of a square, right? Take that square, treat it as a layer, turn it into a canvas, a texture, upload it to the GPU, and then go do some stuff with it, right? So go send the GPU some commands, because instead of copying it back and forth from the GPU's texture memory all the time, what we can do is we can upload it once and then say, hey, GPU, this thing isn't going to change. You can do stuff with it quickly. This is an artifact of how the way 3D games have been built for the last couple of decades. This is exactly how they load textures up early, you know, that loading screen. They load textures up early in the process of getting your game up and running, and then they don't do anything to them except say, it's here, now move it there. And the GPUs have gotten really, really good at going from here to there. So we're relying on a couple of decades of hardware engineering to go make drawing the stuff on your web page buttery smooth by doing the exact same thing that the games that you love do. Okay. So in WebKit today, GPU acceleration has a couple of meanings, right? There's the low-level punch down a hole to the graphics card directly, and then take draw calls and do whatever with them. That's what we're doing with OpenGL, WebGL, and Canvas. And then there's the high-level, go animate me some big thing. That's what we're doing with 3D CSS animations. We're saying this is a big thing, a big square thing. Please go treat it as a texture and manipulate it. This isn't the end of the road. There's a lot more room and opportunity for optimization here. We can turn a lot more of those draw calls that we were talking about earlier from that render tree into things that go directly to the GPU. All those opportunities are open, and WebKit will get there. And it'll be up to each individual port to do it. Okay, and as a result, the compositor thing is up to each individual port to do it. So how can we see what's going on, right? There's sort of now two styles of drawing that we know about. There's the regular, some process comes along, looks at the render tree and says, aha, what's different about this? I need to render this bit. I'm going to go paint it out and then send it to the graphics card. Or there's the part where it's like, I'm going to upload something to the graphics card and then tell it to do something. We'd like to see both variants of this and see how they interact. In Chrome, anyway, there's a handy command line flag for looking at the first one of these called show paint rects. There's a similar available flag in Safari if you enable the debugging menu. Now let's go quickly fire up Chromium with this. Come on. I have a clean build of Chromium. All right. Yes. Show paint rects. So this is going to launch me some Chromium. This is the debug build, so it's a little bit slower than normal. And what I should see here is if I go to, say, scroll, let's say, news.google.com. Great. If I go to Google News here and I start scrolling, you'll see these little lines happening at the bottom of the document there. Can you see those? Each one of these lines here at the bottom indicates the boundary of a new paint area, which is to say that for the old stuff where the lines are sort of overlaying it, that stuff we didn't have to redraw. Interestingly, the stuff on the left-hand side there, the stuff that's in that navigation, because it's floated, and because the float rule means that I have to go paint it over everything when I'm done, every time it's getting redrawn, right? So what we're seeing here is that we may be slowing down scrolling because we have something that's a floated element. This is actually one of the key reasons why float doesn't work well on mobile versions of WebKit today, because it's really expensive to paint. It's expensive to calculate and it's expensive to paint. So what vendors have done is they've just sort of said, none for you. Okay. So watch what happens when I resize it. Note that the resize caused the entire thing to redraw. Right? All those little lines are gone. That means that we redrew the entire thing the whole time. Now, if I go hover over one of these, you can see that hover there, the little box that gets created around the thing that I just hovered over and left, that means that I only had to redraw that little bit. To get to 60 frames a second, you want to be redrawing as little as possible in your document. That means that setting styles on the body, changing a lot of stuff in large scope in your document is going to cause things to be slow. FYI. Okay. So that's regular painting in a nutshell. There's another kind of painting, though. We talked about GPU acceleration. So I'm going to come in here in my Chromium and say about flags. Ooh, flags. And now in Dev Channel Chrome, there's this GPU accelerated compositing, which I've previously enabled. I restarted Chrome. Life is good. I'm going to restart my Chrome, though, in order to come back here and say show repaint rects. Oh, sorry. No, I want show composited layer borders. All right. So now what I'm going to do is I'm going to load this presentation in this Chrome. And because I know, I think, I didn't fail entirely. All right, sweet. Wow, look what just happened here. I'm gonna do this again. Do you see how that thing got a border around it and then it went away? What happened was, while those things were animating, they were given their own layers on the GPU. And then when they were done animating, those layers were freed up, allowed to be reclaimed on the GPU. That memory from the GPU was freed. And then we got one much larger area for the entire slide contents. That much larger area is now the texture that's going to be animated when I animate something. All those smaller textures that might have been occluding it or sitting in front are no longer independent textures on the GPU. So when you hear people talk about that sort of transform 3D hack for CSS animations, what they're really doing here is saying, in an environment where there is a GPU compositor, which is a flag that some builds of WebKit don't have enabled because, again, that backend is hardware and platform specific. What you're doing is you're trying to create one of these layers. You're just creating one of these things, which is going to be independently treated on the GPU as a small area which you can do something with, which means that drawing it is a small operation. It's something that's happening internal to GPU memory, if there is such a thing, and it's happening with a very low rate of communication between the main CPU to say, please go animate it this way, and the upload that previously happened for the contents of the texture. So we can see the same thing happening here, right? Each one of these things that's animating here, even though this is a debug build, it's pretty smooth. And it's pretty smooth not because my CPU is fast, but because this is all happening on the GPU as GPU layers. Does that make sense? All right, sweet. Okay. I want to leave you with one last thought, which is that I've talked to you today a lot about how different versions of WebKit can diverge from each other. But what I think is a primary concern that we all have, and I think is in the back of our minds, is when we talk about building web applications, do we mean web applications of the future or web applications for the browsers we have today? And the relationship between those is not necessarily clear. And so I think we have two things that we should be asking browser vendors for. The first is, what's the feature set in your next release? And the second is, when is it going to be gone? Which sounds like a strange question to ask, but what you probably care about when you're developing a new application is, what's my addressable market? Which is to say, how many of the people who I'd like to see this app are going to see it in its best possible shape, in its best possible form? So say asking for GPU acceleration is a great thing, but asking for today's GPU acceleration may not be good enough for tomorrow's application. We might want to do a different style of GPU acceleration in the future, both when hardware devices and the drivers underneath them support better variants of it, and when we provide better APIs for you to be able to get to them. Hacks should go away over time, right? They shouldn't be with us necessarily forever. So yeah, let's start asking this question collectively, and I guess I'll take questions now. Sorry for running as long as I did. Oh, sorry. Yeah, there are mics in the aisle if that's cool. If not, I'll just repeat the question.
So what are your recommendations regarding
Oh, the question was how do you deliver stuff in the first packet? Have very little in the top of your document. Don't send many headers, and gzip what you can. Right, you need that first packet. So that's unfortunately down to MTU between the device and your server. Usually that's 1,500 bytes, which isn't a lot. So that's smaller than most sets of HTTP headers if you're sending a lot of cookies. So don't send a lot of cookies. Don't send the full 4K down if you can avoid it. And then at the top of your documents, see what you can get in there for making sure that there's enough information to go start prefetching information for the browser. Does that make sense? Cool. Brad.
So I know the Webkit render frame addresses and also the canvas acceleration handling. Is that something upstream in Webkit that might show up in mobile?
So the question was the request animation frame, was that the first thing you were? So the question was, there's a couple of new APIs sort of showing up in Chrome and WebKit. One of them is a version of an API that Mozilla pioneered called Mo's Request Animation Frame. We're doing a version called WebKit Request Animation Frame. But the basic idea is, you know how we talked earlier about how if you go ask for a result before, at an inopportune time, and it's a synchronous call, we're going to lock the renderer. We're not going to do any work while we're calculating your result, so your UI gets janky, right? That's the fastest way to drop your app below 60 frames a second. What we'd like to do is schedule that work for some time when we know that we've got a good answer, we've got a clear shot at doing work without causing readback. Mo's Request Animation Frame is a way for the browser to tell you, hey, here's a good place to go do some DOM manipulation. So yes, that is happening upstream in WebKit. The second question was about specific GPU acceleration of the canvas element. Like everything else in WebKit, what's happening is it's happening on two sides. There's a Chrome component where we have our own out-of-process sandbox GPU architecture, which most other WebKit ports don't share. We spend a lot of time doing security work that most other people don't. And as a result, we have to sort of build this line in the middle like we do for V8 and JavaScript and for the cache system. And then we have the interface on the WebKit side where if you call into some API, there's if-defs around it so that we can proxy back out to whatever the faster version is. So it's happening in both places. But yes, other ports should be able to use it in the same way that we're able to use the compositor that I just showed you, which was the result of mobile WebKit work from Apple. Was there a question back there? Oh, okay, yeah.
From a browser's perspective, how costly is it an operation to render non-semantic markup?
The question was, how expensive is non-semantic markup? Meh. Just markup. Yeah.
You mentioned for JavaScript clients for Windows do get deferred so that browsers can go on process for a set of pages without waiting for them. When do JavaScript actually just get run?
Good question.
Wait until the entire page is done loading?
Good question. So between defer and async, what actually happens with the execution model of the script, right? It gets pulled in at some point. There's two attributes, defer and async. You can use them together. You can use them independently. Async is effectively a promise not to document.write. It says, call me in whenever you get a chance. Don't wait on me. I'm not going to document.write. Defer says, call me back just before onload, right? So wait for the onload event for me to come in, but you can unblock some stuff waiting on me. Like I don't need to execute right now. Now that doesn't necessarily mean I don't need you to request me right now. So you need to use async to sort of control the network behavior and defer to sort of have a handle into the execution behavior. Now remember, neither of those prevent parsing eventually. So pulling in your script as comments and using the hacks that the Sprout Core and Gmail mobile guys used might be the way to reduce that overhead too if you're measuring. Yeah, Dylan. Yeah, the question was, have we thought about implementing a don't parse flag? It's a tricky question because how are you going to get a handle into the evaluated content when you need it? I think there's some hope that with the new simple modules proposal before TC39. So I also am a Google representative to the ECMAScript Standards Committee, the guys who are sort of puttering around JavaScript, the language. There's a proposal before the committee, which I'm in favor of, which adds a module system to the language, which will allow us to both synchronously, from the perspective of the content, do the right thing with regards to satisfying dependencies, which gives us a good execution model, but make it asynchronous potentially with regards to the network. And I think that's going to be the right answer. Internally to browsers, we don't parse much that we don't need to, especially in V8. There's actually large portions of your program that won't be parsed until you execute something. There's easy ways to defeat that. I don't recommend that you go walk the objects that you think you needed. Yeah, Brad. The question is, how fast will CSS3 Flexbox layout be relative to other layout modes? It'll be table speed. It's roughly the same complexity, but depending on what you do. I mean, the implementations haven't been great in WebKit so far. They're getting better. About a year ago, we did an experiment, and it was pretty bad, and we just sort of dusted it off, and it was pretty good for a pretty big app. So, yeah. What is the fastest layout system? The fastest layout system is anything that the browser does and not your script. So let's leave that as the baseline. So if you're doing layout in JavaScript, please stop. Like, I mean that in all seriousness because, again, as we talked about earlier, you're potentially going to be on the UI thread because there is no background sort of multi-threaded JavaScript. So anything you're doing in JavaScript, you're blocking layout and rendering. So don't do that. Let the browser do the work for you if you possibly can in any way. Beyond that gigantic step function, the absolutely positioned layout system is probably going to be the simplest for the browser to compute. But again, if that puts you back into the world of computing your own layout, I don't recommend that. So it's a trade-off, but yeah, let the browser handle it. Keep your DOM shallow. Keep your CSS nimble and expressive. There's a question up here, and I think, are we close to out of time? Yeah, okay. Yeah, last question.
We have single document web applications, which is a lot of the model that a lot of you see kind of applications. The memory fills up fast. Is there recommended or is there a way at all to flush it out without using paper fresh?
Yeah, so the question was, is there some way to sort of like GC all the stuff that you're not necessarily using right now? So there's an ongoing process of attempting to find places where our GC heuristics aren't good enough. The browser does attempt to sort of manage memory for you. There is a question in a very long-lived page about sort of memory fragmentation. We've moved to using allocators that are better about that than they used to be, so that's helped a lot in the last couple of years. Switching to tcmalloc and then in some cases jemalloc has helped significantly in terms of reducing that memory footprint potentially. The other big thing to do is, again, to not leave code resident that you don't need. We do process the JavaScript. We do parse it. We can throw away a lot of the parse tree in the AST, but we do need to keep around the compiled segments, right? We do need to keep around that code. So please load code carefully. Don't load a lot of code you don't need. The same is true for CSS. So basically, the smaller your content is, the more browser-provided APIs you're using, and the smaller your content is, the better off you're going to be. But in terms of like loading your data model stuff, just don't keep reference. Unfortunately, today, my advice is all bad because there's no weak reference type in the language. There's talk of adding it in ECMAScript 6. I'm supportive of that work, and I hope it does happen because we definitely need something to, at least from the stuff that we're actually doing in script, we need a better way to handle it. All right, I'll answer a lot more questions both on the panel and then later. So thanks for your time and attention.